All right, folks, I'm ready to get started today. Welcome back, everyone. Welcome back to the beginning, the continuation of the second part of the course. We did start it last week post the first exam. As you know, I've already graded the exam. I sent out the results to you. So by now you should at least have an understanding of how you did, and also of the curve that I developed based on your performance. So the class average was 63.69, which is actually a little bit higher than my other class. I thought the other class was going to knock it out of the park, but the few that I graded last week before I saw you guys were just like the good ones. And then it kind of went the other way. But you guys actually you wound up doing a little bit better. I mean, in the end, like all classes up until this point have always wound up somewhere in like the 60s, as far as like the average for the class for the overall scores, which appears to be pretty standard in econ classes in general. So nothing surprising here. The standard deviation, the average amount of deviation from the average was about 18 points. So roughly everybody kind of wound up in the 45 to 81 range. The highest score being 91, the lowest score being 16. So there's definitely a decent amount of variation there. A good amount of people at the top, a good amount of people in the bottom, and a good amount of people in the middle. Kind of establishing sort of like a normal type of curve, which is what you would expect in this sort of class and these sorts of exams. So first of all, congratulations to everybody that wound up in these two brackets there. Good job. Obviously, you managed to pull yourself far enough ahead from the rest of the class to, earn those grades, which is really good. Maintain that. Don't change what you've been doing. Keep doing what you have been doing. For those people that wound up in the middle, you're like right at the cusp of doing better. You're doing all right. You're getting by, but it's not quite where it needs to be if you're looking to get an A or a B in this class. So you need to up your game. You need to increase your dedication to the course. You need to spend more time thinking about this stuff, essentially. And if you wound up in the lower brackets there, definitely you need to completely change what you're doing. You need to take a completely different approach. Remember, when I'm talking to you guys, I'm talking to everybody, not just the people in this room. So I'm going to assume that, some of the folks that wound up in those categories are the people that are not here today and haven't been here the entire time. There are people, though, that choose not to come on a regular basis, but still are like watching my lectures as though they're coming to class. Like they're taking my advice with respect to how to approach this course, even if you're not coming to class regularly, and they're doing well. There's a few people like that, but in general, the people that are not showing up to class are generally going to be the people that are not plugged into the course, and therefore, in the end, they're just trying to like figure out a quick way to pass the class, and there's no quick way to pass this class. There just isn't, and so they wind up in the lower brackets. If you are a person that's coming to class on a regular basis, and you wound up in these three categories here, it just means that you're dedicated, but you're not dedicated too much beyond like the actual exposure to the material with me. Like I've said from the beginning, you need repetition to learn this stuff. You need to expose yourself to the material several times via the in-class lecture, taking notes, going back home, going through your notes and the lecture one more time, reading the book, and then making little study guides for yourself based on everything you've covered, including the problems on the homework, and then kind of having it all figured out by the time exam time comes around, so you can just review that stuff prior to the exam and do well. So again, like the people over here, well, definitely the people in the middle, you're fine, but it's all right, like it's not as good as it could be. But even like the people up here, like you have to understand like that, you were curved, right? So you did really well and you should be proud of yourselves, but like there's no curves in the world beyond, college. Like there's no curves. You're out in the world and everybody's out there with you. Everybody from every walk of life, everybody from every school. Um, and even though you might be a person that like is really dedicated to what you do here, you're gonna meet your match, and you're gonna meet your superiors beyond this place. Like you're gonna meet people that are so freaking driven that they are willing to do anything to succeed. And you're going to need to up your game as well when you get out of here. So don't get too comfortable here, even with your like great performance in classes like this. Um, Always keep challenging yourself. Always strive to be better, no matter how good you do, because there are people doing better out there, and you can be as good as them. You can be better than them. It's very possible, and all it takes is like that dedication to being that person, and constantly working at it every single day. So just don't get too comfortable, and especially the people that will get by this course via a curve like that. That it's a very easy thing to do in these classes that are curved, like to kind of just like get by, and then you kind of have that approach overall. You kind of adopt it as like, okay, this is a means of getting through here. But again, once you hit the real world, like no more curves, no more like safety nets. Like you have to be ready to like really put everything you have into what you do in order to be able to move your way up in the social ladder, which is there. It's possible to move your way up, but it's challenging. And again, you're going up against everyone, not just people that go to CSUN. You're going up against people that go to Ivy Leagues. You're going up against people that go to like UCLA, USC, Berkeley, and again, like nobody in those, regardless of what's been implied by our society and the messages we've gotten, they're not better than anyone that's here. Like in no way are they any better. Inherently, but they're better at pushing themselves really far. And so again, it's about like you figuring out, how do you get yourself to be that person? How do you get yourself to be that person that, regardless of the task that you're given, you are ready to take it on and take it down. You will not like settle for second place. You will be the top no matter what. And that is what you go for. And you do it the right way, by managing your time properly, by sacrificing those things that are distractions that are enjoyable now, but can, again, like kind of set you on the wrong path if you sort of overindulge in those things. Does it mean that you can't enjoy your life now? No. Does it mean you won't enjoy your life later? No. It just means like you need to be able to make this your priority. And if you do that, and if you succeed here, and you can cultivate that personality, that person that is like always ready to take the world on, then the life can continue to be fun for the rest of your life. Like you can continue to have really wonderful moments in your life that you balance against the really hard, strenuous moments that require a lot of work forever until the end, until the very end. Versus like you get out of here, you can't find a great job, you take whatever you can get, then you're miserable at that job for an indefinite amount of time, and then you're just like unhappy. And then you barely have time to enjoy your life because, you have some job that barely pays your bills. And, I mean, that's just the reality, folks. It's just the reality of the situation. Like this degree that you get here is ultimately like just going to be something on your resume. What's really going to have value is who's inside of you. And also, as you get older, like what's outside of you starts to fall apart. And so if what's outside of you is something that society tends to value and will get you certain places, or get you a certain amount of positive treatment from people, that goes away as well. Like that eventually goes away. And if you don't have what it takes inside, that thing that will carry you through your entire life, all those successes, then things cannot go so great beyond this place, and like all the ideas you have about what this all can mean for you will be meaningless. And it's like, again, it's not about grades in this class. It's not about like pleasing your parents or your professors or your peers. It's all about like becoming the best person you can possibly be, and always like being ready to just not let yourself down, knowing that you've gone through all sorts of challenges here, and that you never let yourself down. You always were there to make sure that you got through the challenges, you conquered the challenges. And if you have that, if you develop that pattern, then you have the most valuable thing you could ever have in this world, which is like confidence that regardless of what's going on in your life, regardless of what life is throwing at you, that you are ready to take it on, that you are ready to do whatever it takes to succeed, and that you will not let yourself down, that you will keep pushing yourself until you get what you want from this world. When I was in the PhD program, it was miserable for 5 years, 5 straight years of misery. Every single day, waking up like, oh God, I'm still here. I'm still doing this. Like endless work, endless work. On top of the stuff that life was throwing at me, the other stuff that life just kind of throws at you out of left field, and it was very easy for me to have walked away at any given point. But I knew that no matter what I was going to get through it, I knew that no matter what I was going to get myself to succeed in this thing that I'd taken on that was like nearly, conceptually impossible to succeed in. Because I had always done that, because I did that through college, because I did that when I got out of college and eventually figured out, okay, this is exactly what I want to do. And then figured out, okay, this is exactly how I'm going to do it. When I got into the master's program in economics, having a degree in film only, having taken, math courses or whatever to get into that program, and then going up against like really top-notch people that already like were good at economics, whereas I didn't know anything. But I took that on and I took it down, and I knew in the PhD program that I would do the same thing. So I was able to just kind of stay in the moment and just like take on the tasks as they were given to me, and just like work every single day, all day long, as much as possible. And I got myself through that, and it's done, and I'm really happy about that. And now here I am, and like there's so much to look forward to for me. Like all I see is opportunity. All I see is like flexibility with what I can do with my life. I don't feel like I'm like kind of in a corner where it's like I only have a couple of options and they suck. And no matter what, I'm going to be unhappy. It's like, no, it's like I can go this way, yeah. I can go that way, yes. I can go that way, yeah, pretty good. All these options are great, and like it's all because of the work that I did, and that kind of thing can happen to anybody. I come from nothing, like I don't have. My family they're immigrants, like they're poor people, like we didn't have anything. I just built myself up, and like I'm happy where I'm at, and that's most important. You have to be happy in your life, so you want to put yourself in a situation in your life that will make you happy, and the way to do that is to again build as much value inside of you as possible, so that people value you enough to give you opportunities, to give you the options. You can then decide what you want to do versus being pushed into some cubicle for the rest of your life and just being miserable. So work really hard here. This matters. Like it's not just like some crap that you're forced to do because of whatever. Like it's meaningless. No, it's not meaningless. There's a lot of meaning to it, and a lot of it just has to do with like what it does to you as you push yourself, as you go through the process, how it forms and kind of shapes you into that person that's just like ready to take the world on, that people can identify out there as a person that's ready to take the world on, and a person that they can depend on, a person that they know that if they give you an opportunity, you will enhance their organization, whatever that is, versus like like be some kind of like a drain on them, or even kind of cripple them. And that's not something you can fake. Like that's not you can talk your way through an interview. You may even talk your way through the front door of a place you want to get to. But once you are in there, you cannot fake like being like that person, that go-getter, that like I will take care of things, I will figure things out, I will excel at what I'm asked to do, and I will do more than what I'm asked to do. You can't fake that. Like you can't talk your way into that being that person. And that is the person that gets moving higher and higher in this society, that gets the opportunities, that gets the things that you guys want out of all this. So work hard now, every single moment, and you will build that person. Some of you are already there. Some of you are already there, and some of you already know all of this. So I'm not telling you something you don't already know, but it's good to hear it from other people because you want to be reminded. You want to hear it from outside. So that's why I like to give these speeches. Like post exams, like just kind of light a fire under you, just like kind of remind you of like why you're here and what this can accomplish for you, versus you just kind of going through the process and then kind of letting it kind of take you down, given the weight of it. You have to stand up to it. You have to show it what you can do, what you're made of, and then ultimately show the world. So work really hard. It's not the end of the world if you didn't do that great on the exam. There's still more exams in this class. There's still paper, etc. There's opportunities to bounce back. But now that we have established a curve, there is a curve in the class, and thus the entire class will be curved. And so, if people landed at the top, they've staked a claim to those spots. Like, you have to fight for those spots now if you're not in there. Is it impossible for you to get into those spots? No, it's not impossible. But you've got to work really hard because there's some strong people in this class, and you need to rise up to the occasion in order to be as strong, in order to earn what you want to earn out of the class. And if you're down here and things aren't looking too good, it's the beginning. Like, don't let this define the experience for you. Like, it's just it happened and it's in the past. You're in the moment. Do what you can now to like turn this around. It's possible, very much. Don't get discouraged by it, even if you wind up not doing well in the class overall. Don't get discouraged by it because it's not a reflection of you or your ability or your character. It's just a reflection of the fact that you just didn't put in enough into the class, and you will know either because of this exam or because of your performance overall in this course that you need to change something. And if you do change that you can get that better result, and that it is ultimately all in your hands, and it is not out of your control. Like, these things are not impossible. These classes are not beyond your abilities. You simply you're not able to push yourself to the extent that you need to push yourself. And the only way you're going to do that is by pushing yourself. That's it. Nobody else is going to do it for you. Nobody can teach you how to do it. Nobody can show you how to do it. Like, you need to do it yourself. And that is the only way that all of this will mean anything for you, regardless of whether this class goes well for you or not. But at this point, there's still a lot of hope. Work really hard and turn it around, and it will turn around. And that will make me happy because I want everyone to succeed ultimately. That's why I do this, because I like seeing people kind of surmount challenges and me kind of playing a role in that to whatever extent I can. And so please, again, it's not about me, but hey, if you want to make it about me, I'll be really happy if you wind up turning it around. So do that. But overall, you all should be proud of just the fact that you are here, because it is a choice that you are making to be in college, and you've made it. So now you need to just kind of make the best of it. A lot of you are already doing that, and my hat is very much off to you. And I respect you. I respect everybody, but those people that are really putting in the effort that you need to put in a class like this, you really make it all kind of worthwhile for me, because again, I put in a lot of effort into building these lectures and making sure that everything's as clear as possible. And the people that actually are interested in doing exceptionally well and putting in the effort and being dedicated, you validate the work. And so I thank you for that. And everyone else, again, you're not any worse than the people that are at the top. You just haven't quite figured out how to push yourself that extra distance to really get to that level. And you can, and I hope you will. All right, so that's basically the exam. So how the curve works is I target a 70 for the class. So the average was 63.69. So I target a 70, and then that gives me a number that the exam would be out of in order for me to have a 70 average in the class. I forgot what it wound up being for you guys. I think it was 88 or 89 or something, maybe 90. And so your Moodle score is a percentage, and your actual score is going to be the score that you got on the exam out of 100 points. But once I figured out that number, I took your score, I divided by that other score that I needed to get the 70 average. That got me a percentage. I multiplied it by 20, which is what the exams are worth. They're worth 20% of your grade, so 20 grade points, and that's what your Moodle score is. And if people wound up getting a little bit more than that number that I targeted, then they wound up actually getting a little bit more than 20 points on the exam. There aren't many people that got it on this exam, but that's always in play. So it's always possible to actually wind up getting more points than the exams are worth. So for those of you that are looking to make up some points, like just kill the next couple exams and things should work out. All right, so I'll pass back the exams at the end of the day, not at the end, not during the break. At the end of the day, I don't want people looking at exams while I'm lecturing. I don't want questions about the exam. I posted answer keys. Just check your exam against the answer key. If you think that I made an error in the grading, which is possible, I grade fast and a lot, so it is possible. If I did that, just write it up for me. Bring it to me in class next time. Submit your exam to me with the explanation, and then I will look at it. I'll address it, and of course, I will fix any problems if there are any. And that's how I'd like you to go about doing that. Are there any questions about anything before I actually move forward with the material? Yeah. If I finish chapter 5, I'm likely to finish chapter 5. But if I don't finish it, I'll still make it available. But I'll make the due date further, like the end of next week. But I won't set it up till tomorrow. Yeah.
Was it the easiest test?
Was this the easiest test out of the 3? Well, no. I wouldn't say any of them are any more. Well, the last one is a little bit more difficult, I'd say. Yeah. The middle one is all right. I mean, they're all kind of based on ideas that you've already covered before. But the last one it goes a little bit further. So that I think maybe the last one's a little bit more challenging. That's why I don't make the final cumulative. But ultimately, the ideas do build upon prior ideas. So to an indirect extent, it is cumulative. But yeah, the level at which you're being challenged is basically the level that you'll be challenged going forward. So, other questions? Yeah.
Do you ever plan on recording the thing you tell us right at the beginning of class and uploading that as a pre-game thing? That's a good idea.
A pre-game.
Yeah, so you can hype this up when we're at home.
But okay, so like I'll lecture, right? Oh, you mean like before you come to class?
No, like for any other class. You sell it. You're very inspirational.
Okay, well that's very nice of you to say. I mean, I just talk. I don't have a plan for the talking. I just talk. It's all there recorded.
I mean, you're not recording what you did in the beginning.
I am recording this, yeah.
Oh, all of it.
Yeah. So I'll be there. You want to listen to it again on a loop indefinitely every day.
I plan to. That's my alarm clock.
Well, it's a good way to wake up. I like to wake up to myself. Anyway, all this stuff is recorded. It's there. Ultimately, I just want everybody to succeed. And again, I can only do so much. So just you have to play a big part in this. And so play the big part. Play the big part that you can play and are expected to play. And just make the best of this whole thing. All right, let's move forward, folks. We started talking about production last week. And this whole chapter is about production and cost. So like I said last time, we are developing a framework that is going to be the basis for analyzing optimal decisions by firms in a variety of competitive contexts that a firm can operate in. So it goes all the way from the perfectly competitive case, which is as competitive a market can be, to the monopoly case, where you have just one firm dominating the market. So we'll consider each of those two cases, and then we'll consider the in-between cases, which are the monopolistic competition case and the oligopoly case, which I'll talk more about when we get to them. and it's all about sort of figuring out like what is the best way to go about selecting the amount of output and pricing in order to maximize profits. But in order to do that, you have to have a framework of what costs are, because anytime you're considering any decision with respect to like a quantity of something to do, like how much should I produce, you have to look at marginal benefit versus marginal cost. The marginal cost is going to come from the total cost function. It'll be the derivative of it. We'll cover derivatives today. And in order to understand total cost, you need to understand where those costs come from. And so we start this chapter by kind of modeling a very general production process that has very specific characteristics that are very general, and then they will translate into costs, and then that will get us the framework that we need to make the decisions that we'll be analyzing moving forward. Yes.
Since diminishing returns have nothing to do with margin, because diminishing returns only affect the actual negative past the highest point, right?
So that's not when it goes negative. That's when it starts to decrease. So the extra amount of output produced by hiring additional folks starts to decrease. I'll go over that all again today. It goes negative when it actually when you hire a person and it starts to decrease the amount of output overall. Whereas with the diminishing returns, we're talking about like additional people producing additional amounts that are positive, but less than the prior person. And that is marginal product. So that's extra output that's produced by employing additional folks. And that is actually going to be directly related to marginal costs. And I'll establish how that is today in the second part of the course. So yeah, actually marginal product will lead to marginal costs. So it's all related, and you'll see how it's all related if you're plugged into the whole lecture today. And so once we have the cost down from this chapter, there's two chapters that we'll cover next week. Chapter 6 and 7. Those chapters are smaller, they're less abstract, not much like modeling, more of like kind of like insights. So like the first, like chapter 6 is about like, well, how does a firm practically go about selecting their inputs in order to minimize costs in practice? So we'll deal with like some of the practical issues associated with that. And then chapter 7 deals with the nature of industry. So like what makes one industry more competitive than another industry? And sort of like what are the characteristics of that? What are the kind of fail safes that we have in place in order to kind of curtail the lack of competition? So a lot of kind of practical issues in the chapter 6 and 7, which wind up being a really good basis for people that aren't very in tune with the abstract and would prefer to kind of use practical information to analyze your cases for your paper. So those are good chapters for mini papers. So if you haven't knocked out the mini papers yet, you should start to. It's a good idea to get them done sooner rather than later. If you have some free time right now, in between exams, in between your other midterms, like knock out some of these mini papers, write them. It winds up being a lot better for you towards the end of the semester. You basically have the paper done already. It takes you no time to like put it together and submit the final paper. Most people that do that are really happy about it at the end, because in the end, that's when everything piles up on you. And so if you work on this stuff now, knock it out, then you'll avoid being back into that corner, which is uncomfortable and will lead to bad results. Like your papers will not be good if you do that. If you're like one of the people that there's usually a third or a half of the people that wind up like writing 3 mini papers in the last 3 available options, and they're just writing to write. Like they're not really thinking about what they're writing, and it winds up being not that great, aka crap. So don't write crap. Write good stuff by taking time now and hammering out some decent mini papers. And again, chapter 6 and 7 are good for kind of just using practical insights to explain or analyze some aspect of the case that you've chosen to write your paper on. So make sure that that's happening as well. Um, and yeah, so we'll likely finish most of chapter 5 today, if not all of it. And of course, we'll have our break as we usually do, and that's that. So we'll continue talking about production. We've started talking about production, but we only started talking about production in the short run, and we need to talk about production in the long run. The distinguishing factor between the two being the fact that in the short run, there's at least one factor into production that's fixed, that the firm cannot vary. They cannot change it. So they buy their factory or they rent their factory for a certain amount of time. They buy their machinery for a certain amount of time, and they're locked into that. And because of that, their workers are limited by that. But in the long run, the firm is free to adjust all their inputs, both labor and capital. So then the question is, how much of each should they use? And so we have a framework to analyze that, which is going to be very similar to the rational consumer choice model framework that we use to analyze the decision to consume by consumers that was behind the demand curve. And so if you understood like the mathematical basis for how all of that worked, it's essentially the same for the firms choosing their combination of their inputs to minimize their costs in the long run. So if a lot of those insights will help you to understand that model. So ideally that is still kind of fresh in your mind, and you can translate some of those ideas that are really properties of that approach to this version of it in order to maybe digest it a little easier. And then once we've established that, we'll go on to the cost function, which is essentially the result of your understanding of production in the short run and the long run. And then we'll talk about the various aspects of the cost function and the various costs that we can derive from the cost function that are going to be relevant to making optimal decisions by firms. And that'll be it. There's an ancillary subject at the very end that has to do with a production processes that involve multiple outputs, multiple different types of goods. And that's the one thing that we may not cover. It might cover at the beginning of next class. Nonetheless, if we don't finish chapter 5, I will open up the chapter 5 homework just so that you have it available, because next week we will cover 2 chapters, and so there'll be 2 homeworks for those chapters. So there'll be a lot of homework piling up. So just if you want to get ahead, I'll give you the opportunity to do that. Yeah.
For the mini papers, 67 papers too. Are you going to get 2 weeks for
It's still going to be the 1 week. Yeah. Actually, maybe I will give you an extra amount of time. Yeah. Maybe I'll give you like a week and a half. Maybe like a week and a half. Yeah. Yeah. Not today, no. Yeah. Yeah. At the end of the day, I don't want to do anything. So I start lecturing in the morning at 9. So this is like a long day for me. So I'm done when you guys are done. But tomorrow at some point, yeah. All right, so previously we started covering production. So we started just talking about the general specification of how we model production, which is a relationship between the amount of output that can be produced given the amount of inputs that are used. We assume that only 2 inputs are used in the simple case that we consider, and that is labor, of course, workers, and then capital is kind of the catch-all category for everything else used to produce. Generally, we just think of it as like people-made things like factories, machines, etc. So you can just have a general sort of relationship between those inputs being the independent variables and then output being the dependent variable. And then we'll have specific versions of that relationship we'll consider that capture different characteristics of different production processes. There's, again, the difference between the short run and the long run, which will be relevant both to costs as well as to the firm's ability to choose their inputs. Because, again, in the short run, what defines the short run is that some factor of production is fixed. We generally assume capital is fixed, but there is one homework problem that assumes labor is fixed. But beyond that, we assume capital is the fixed input. So if we fix capital at some amount, K star, then then output is just a function of labor. So that's the short run production function. And in the long run, all inputs are variables. So a firm is able to, in the long run, say, oh, well, my factory space is not enough. I need to expand it. How much should I expand? We'll figure that out later. All right, so firms need measures of productivity to figure out how things are going, which then informs their costs, which then informs how they're going to maximize profits in their industries. So one of the measures of productivity is, of course, the total product, the total amount that can be produced, given the inputs that are available. There's the average product at any given amount of an input of labor or capital. There's an average amount that's being produced by each unit, right? So the average product of labor is just the amount of output divided by the amount of labor at any given point. And the average product of capital is the amount of output divided by the amount of capital at any given point. But of course, sometimes we are just interested in how much is total output going to change by employing one more unit of an input, either capital or labor. And that is how we get that information is through the marginal products. So we've got the marginal product of capital, which is the change in output with respect to a change in a change in the amount of capital that's being used. We assume that it's just one unit, and this is also a good estimate of the derivative of the production function with respect to capital. So how is output changing with respect to capital? Well, you take the derivative of the production function with respect to capital, and you get the marginal product of capital. We'll talk about derivatives in a second. And then marginal product of labor. Again, if you hire one more person, how much extra output will you produce? Marginal product of labor. And it is the derivative of the production function with respect to labor. So we talked about this very general production process that we model as kind of like the standard case, where you just imagine like a firm just starting up. They have nobody working. They hire one person. That person does everything. So if you hire a second person, they start to divide up the tasks, specialize, division of labor. That means that efficiency is improved. That means that marginal product starts to increase, meaning that the extra amount of output produced by employing additional folks is greater than the last person. So over that range, you have increasing marginal returns to labor. So just based on what we assumed of this production process, up to the fifth person, you have those increasing marginal returns to labor. So again, each additional person hired produces more than the prior person because you are dividing up the tasks and becoming better at producing. But because of the short run, because the short run, again, is defined by the fact that there is a limitation on one of the inputs, we assume it to be capital, then the workers that are hired wind up kind of hitting that short run wall where there's only so much factory space to go around. So they start getting in each other's way. There's only so many machines to go around. So they don't have enough tools they need to produce as much as they could if they had more. So even though hiring additional people will yield positive levels of output, so the marginal products will be positive, they will be diminishing. The extra amount of output produced by hiring additional folks after a certain point will start to be less than the last person hired. And that's what this range represents. So this is the range of diminishing marginal returns to labor. And then finally, if it can get so bad that you start to hire folks and they actually start to get in the way of what's happening, and the marginal product of labor is negative over that range, over that range we have negative marginal returns to labor. This blue curve here is the marginal product curve. It's just basically plotting the slope of our total product curve, which is the marginal product. That's the derivative of the production function with respect to labor. So again, it's telling us that between 0 and 5 workers, we've got those increasing returns to labor. So the marginal product is increasing. And then once we hit that short run wall, the marginal product of labor starts to decrease. We have diminishing returns or decreasing marginal returns to labor. And then eventually marginal product gets negative when hiring more people actually reduces the total product. And the other curve we see here is the average product, telling us how the average amount of output is changing as we're moving along our production process, and marginal product is changing. So remember, average at any given point, you hire one more person, that person adds a marginal product, which will either increase the average or lower the average amount that each person can produce, depending on whether marginal product is above the average or below the average. So over this range here, marginal product is above the average, so it pulls it up. So average product is increasing along that range. And even when the the production process hits that decreasing returns range and marginal product starts to diminish, even over that range, it's still greater than the average product, so it's still actually bringing the average product up. And average product is at its minimum, is at its maximum when the marginal product curve crosses it, when they are equivalent. Beyond that point, marginal product is less than average product, so each additional person produces an amount that is less than the average, bringing the average down. So the marginal product of labor is less than the average product, bringing the average product down. And why this relationship is important will become clear when we look at costs, which will be like a mirror of these relationships. And average costs wind up being really important for firms with respect to their profitability. So it's important to kind of understand average product in relation to marginal product, in relation to the average cost and marginal cost. And I'll keep reminding you of those connections as we move forward. All right, so the role of the manager, there's two roles for the manager in the production process. One is that managers make sure that the employees are actually working on the production function. So you have a production function, you know like what you need in order to be on the production function, but can you get your workers to work on that? Well, we talked about how setting up incentives is the most important thing, but like the real sort of science and intuition of that is beyond the scope of this course. So if you're a management major, it's stuff that's covered in more detail in your other courses. But of course, we do highlight that aspect of the job here because it's an important one. And the other one is that the manager pick the right level of inputs to be able to maximize profits essentially. And so we talked about how in the short run, when the capital is fixed, that the firm needs to figure out how many laborers to hire. And the way to do that is to take the approach we take with any question in economics that has to do with how much of something should be done. We look at the marginal benefit versus the marginal cost. The marginal cost of hiring an additional person is their wage. The marginal benefit is the value of what they can produce. The amount they can produce times what that amount can be sold for, which we call the value of marginal product. So to figure out how much extra labor to hire, the firm looks at the value of the marginal product of labor, the marginal product of labor, the extra amount of output produced by employing an additional person, times what that output can be sold at, the price that's set in the market for the good. And if the same question was being asked of capital, if capital was variable, then we would look at the value of the marginal product of capital, which is the same, marginal product of capital times the amount it can be sold at. And so the optimal amount of labor to hire in the short run for the firm is the amount of labor that corresponds to the point where the value of the marginal product of labor is equivalent to the wage. That's where the marginal benefit equals the marginal cost. So this is the value of the marginal product of labor curve. It's hump-shaped, just like the marginal product of labor curve. Again, reflecting the fact that there's increasing returns initially and then decreasing returns to the labor input because of the short run. If you multiply that marginal product of labor curve by some constant, you get a curve that has the same shape. So that's why the value of the marginal product of labor curve is essentially the marginal product of labor curve, just multiplied by the price. So it's got that same shape. And the profit maximizing point happens over the diminishing returns range, because over here you do have this point where the value of the marginal product of labor equals the wage. But because we know we have increasing returns, if you hire an additional person, the value of what they can produce will actually outweigh the cost. And so it makes sense to keep hiring folks. So then you keep hiring folks, and then you hit that short run wall, you hit diminishing returns, And over this range here, still the value of what they produce is still greater than what it costs to hire them up until this point where they're equivalent. And beyond that point, the value of what they can produce, which is the value of the marginal product of labor, is less than the wage, and therefore it doesn't make sense to hire beyond that point. So this is the optimal point. And also the diminishing returns range of the value of the marginal product of labor curve winds up being the demand for labor by a firm. So when you look at labor markets and you see a demand for labor and a supply of labor being, of course, represented by those workers that are willing to work at different wages, that interacting with the demand for labor for an industry or whatever, that demand for labor is being established by this relationship here. So that's what's happening behind that demand curve in labor markets by firms, and this is how they're optimally choosing their workers, the amount of workers they're going to hire. So that's a short run situation. All right, so today's lecture, we looked at the algebraic forms of production functions. I actually covered this last time as well, so I won't cover it. I'll cover it really quickly. We have a couple of different options as far as like what the production function may look like. So using the graphs and using the table, we got the intuition about the production process that we model very generally. And this is about taking it to the next level and actually representing those relationships mathematically. Depending on the equation you choose, that will reflect a different production process with different properties. So the one that we've been talking about that has diminishing returns won't always be reflected in practice, and also therefore not reflected in like an equation that would represent that. So a production function can be estimated the same way that the demand functions were estimated in chapter 3 using statistical regression techniques. And so that will dictate what the form of the production function will look like, given the nature of a production process. Some production processes are going to lie in the extreme cases, one of them being where the inputs into production are perfect substitutes for each other, meaning that you can just use labor, or you can just use capital, or you can use some mix of the two in order to produce a certain amount of output. So that kind of production will be represented best by a linear production function. So you have capital and labor, and then, as I said last week, the coefficients on capital and labor represent their productivities, like their marginal products. So 1 unit of capital is going to be able to produce 4 times as much in this example down here as 1 unit of labor. So labor is 4 times as productive as, capital is 4 times as productive as labor. So you need to substitute 4 units of labor for 1 unit of capital in order to maintain the same level of output. But they are perfectly substitutable as long as they're substituted in that ratio. The other part of the spectrum that could capture a type of production process is the Leontief production function, which is given by this expression here, essentially telling us that the amount that can be produced is going to be represented by the minimum of these two numbers, whichever one is smaller, that's the amount of output that can be produced. So this is called the fixed proportions production function. And the example that the book gives for this type of production function is something like, let's say, a word processing firm where they produce documents, and like you can't just have keyboards, you can't just have people, you need them in fixed proportion. You need a keyboard and a person to increase output. And so that's how you need to hire more and more people, by employing one of each in order to increase output. So K is the number of keyboarders, L is the number of keyboarders, K is the number of keyboards, L is the number of keyboarders. And so then we looked at this example here where we looked at this Leontief production function, and we tried to figure out, well, how much output can be produced with 2 units of labor and 5 units of capital. And so if you plug those in, 2 times 4 is 8, 5 times 3 is 15. So obviously 8 is the minimum of the two, which means that you can only produce 8 units of output given using 2 units of labor and 5 units of capital. So even if you were to increase your labor by one more unit, that's still only going to be 12. And this is 15. So you will be able to, I meant capital. If you were to increase your capital by one more unit, so 6, so this would be 24. Since labor is not being increased, that won't increase the amount of output. So they have to be increased together in fixed proportions. So that's the other extreme case of the possible spectrum of production processes. The least common cases, the one we consider is the most common case, and so we need a very specific type of production function to capture that case. And so in order to do that, in order to understand that case, we need to take derivatives. So that's what we'll jump into now. In order to understand taking derivatives, we also need to understand how to work with exponents. So just here's a review of the properties of exponents for those of you that might be rusty on them. So let's say you have some number b raised to the power of x, and you're multiplying that same number b, but it's being raised to the power of y. This is equivalent to that number b being raised to the sum of the two powers, right? So if this was like 8 to the second power and 8 to the third power, this is equivalent to 8 raised to the power of 2 plus 3, so 8 raised to the power of 5, right? If you have some number b raised to some power x over some number b raised to some power y, that is equivalent to that number b being raised to the power of the term on the numerator minus the power of the term in the denominator. If you have some number b being raised to some exponent x, and you're raising that whole expression to another exponent, then what you're essentially doing is multiplying the exponents, right? So 8 raised to the power of 2, and you want to raise the whole thing to the power of 3, then that's going to be equal to b raised to the power of 6, 2 times 3. If you have the product of two numbers, b times c, so let's say 2 times 4, and they're both being raised, so you have the product in the parentheses being raised to the power of 5, that's equivalent to the first number, 2 raised to the power of 5, times the second number, 3 raised to the power of 5. If you have a ratio of two numbers, b and c, being raised to some power x, that is equivalent to the ratio of b raised to the power x over c raised to the power of x. Any number raised to the power of 1, of course, is equal to itself. What is any number raised to the power of 0? Equal to 1, right? So that's another important property. And then finally, any number raised to some negative power is equivalent to 1 over that number raised to the positive power. If you're rusty on these things and you need to get quick at it, just like look up some properties of exponents problems on Google. I'm sure there's like a bunch of like practice problems that math teachers put up, and just like kind of blow through them for like an hour and you'll get it down. You'll dig out those old skills that you maybe haven't used in a while if that's the case. All right, now let's talk about derivatives. So the main problem of differential calculus deals with finding the slope of the tangent line at a point on a curve. So a line has an easy slope to figure out. The slope is constant. It's the rise over the run. It doesn't change. So it's a really easy method to figure out how that y variable is changing with respect to the change in x at any given point along that line. But if you have a curve that doesn't have a constant slope, that's just kind of moving around, like how can we say at any given point how that relationship is changing? If you change the x variable by 1 unit, how do we know what's happening to the y variable at that point? Well, we need a means for that, and we use the derivative to figure that out. And we use the concept of a tangent line to help us get the understanding of that. So in high school geometry, a tangent line or tangent to a circle is defined as a line that just touches the circle at exactly 1 point. But the idea of a tangent is not very useful for other kinds of curves like this one you see here. It's just touching the curve here, but it's actually cutting through the curve over here. So even though we do use the concept of a tangent line, we need to take it a step further. To obtain an adequate definition of a tangent line, we use the limit concept and the geometric notion of a secant line. A secant line is a line that intersects a curve at 2 or more points. And so we use this concept of a limit of the secant lines, the slope of those lines, to help us get to the approximation of the slope of a tangent line that's just touching a curve at one point in order to approximate how that curve, how that relationship is changing at that point. I'm not going to go through limits in this class, like what that means and how you do them, but it's important for you to understand what they are and that they underlie this method of derivatives. That's why limits are taught to you in like your 103 course, because if you aren't taught limits, then you won't understand why you can use a derivative in the way you can. But I will go through an example of a limit right now of these secant lines. So let's say we want to define a tangent line at point P. So we want to define a line at this point whose slope will approximate what's happening at P as X is changing and how that's affecting Y. So let's say we just have this one secant line, PQ. It intersects the curve at those 2 points. But if we were to move Q, the point at which the secant line intersects the curve beyond point P, if we were to move that point closer and closer to P from both sides, then we would wind up getting slopes of lines that are closer and closer and closer to the limiting position, the point that we're actually interested in, which is that line that's just touching P at the point we're interested in, that will give us the approximation of the rate of change at that point. And so you take the limit of the slopes of these secant lines that approach that point that we're interested in order to figure that out. So in both cases, the secant lines approach the same limiting position. The common limiting position of the secant lines is defined to be the tangent line to the curve at P. The definition can be applied to curves in general. So the slope of a curve at point P is the slope, if it exists, of the tangent line at P. So let's just consider the curve we've been looking at, which is a parabola, which is represented by x squared. And let's say we were just to take the slope of that one secant line that's furthest away from the point we're interested in. Then you just calculate that as you would any slope, the rise over the run, right? So the difference between the y values and the x values. So 6.25 minus 1 over 2.5 minus 1. So that's going to be the slope of that line. It winds up being, in this case, equal to 3.5. Basically telling us that at that point, if you change x by 1 unit, y changes by 3.5 points. This table here represents the slope of that line, of those secant lines, as we approach that tangent line that we're actually interested in, whose slope will tell us the approximation of what's happening at P. So again, the furthest one has a slope of 3.5. As we get closer, we get to 3. As we get closer, we get to 2.5. Closer, 2.25. Closer, 2.1. Finally, we get to 2.01, which essentially approaches 2. Which means that the slope of this tangent line just touching P, which is the limiting position of those secant lines, is approximately equal to 2. Meaning that at point P, if you change x by 1 unit, y will change by 2 units. And this derivative allowed us to get that approximation, even though we can't normally just take the rise over the run from a curve like this. But the fact that we use limits and we're able to get to that result, gives us that important piece of information that we would otherwise not be able to get. This method was developed by Isaac Newton. He spent a lot of time by himself. I think like 60 years by himself. Like he had a servant and that was it. He barely left the house. I heard he was an asshole, like a terrible person. He had students at one point. They hated him. He was a horrible person to them. But in the end, like being this shut-in, it resulted in changing the world dramatically. Like we've left the planet because of calculus. We've created skyscrapers because of calculus. We can fly because of calculus. Like all the things that we can do in the modern age are a result of being able to figure this out. So maybe it's a good thing to be that kind of person, but generally it's not. Don't be that, unless you're going to change the world, which in that case, so be it. Anyway, so that is the derivative. It's the limit of the slope of the secant lines, and it's an approximation of the rate of change of a curve at a point which we call the derivative. I don't expect you to ever explain to me what a derivative is, like why you can do what you can do, but you, as just a person in this world that's using this tool, should know what it is and why you can use it. And you should understand it. And hopefully at this point you do understand it. Ultimately, there are shortcuts to being able to take the derivative of a function, which then gets you another equation generally, and that equation will have a variable in there, x, and as x changes, that will give you a different number, and that different number is going to be the limit of the secant lines, the slope of that limiting position tangent line at any given point that will estimate the rate of change at that point. And so all I need you to know is how to mechanically use the shortcuts to take the derivatives. You don't need to actually understand how or why you can take them, but you should. And that's why I went through all that, because I don't just want to teach you mechanical things. You should know what you're doing. It's been covered before. In case you forgot, I wanted to cover it one more time because it's important. But now we're going to just move forward with just the basic rules of taking derivatives. So sometimes the function that we're going to be considering is just a constant function. It's actually not changing with respect to x. So if c is a constant, then the rate of change, the derivative, which we denote dc dx, in this case, c being the function, which is constant, is going to be 0. Remember, the derivative is an approximation of a rate of change. But if you have a constant function, plotted, it's just a horizontal line, basically reflecting the fact that as x changes, nothing is happening to y. So y f of x equals y is a constant function. So whenever you have a constant function, the derivative is going to be 0 because there's nothing changing there. So the derivative of a constant function is 0. Again, d dx denotes the derivative. Also, some function f of x, you can also denote the derivative as f prime of x, if you remember. Quick examples of the constant derivative. The derivative of the constant function 3, so this would be a line at 3 units on the y-axis, is equal to 0. The derivative of the square root of 5, that's just a number, so that's equal to 0. The derivative of this big number raised to this big exponent is equal to 0 because it's just a number and it's not changing. The next rule gives a formula for the derivative of x raised to some constant power, which is called a power function. So here you have x raised to the power of a. To take the derivative of that, you just multiply the whole thing by the power, the exponent, and then subtract 1 from the exponent. So the derivative of that is, again, x times the exponent, and then you subtract 1 from the exponent. Quick example, you have f of x equals x. So x obviously is being raised to the first power. You don't see it, but it's there. So to take the derivative, you do what you do mechanically. You multiply the whole thing by the exponent, so you multiply the whole thing by 1, and then you're left with x raised to the power of 1, and then you subtract 1 from that. So you're left with x raised to the power of 0, which is equal to, so what's the derivative of this function? It's equal to 1, right? Because you're going to have 1 times 1. So if you just have a variable that's raised to the power of 1, the derivative of that is going to equal 1. If you don't remember that, you could just do the method in order to get you to the answer. X raised to the power of negative 10. You multiply that by negative 10 and subtract 1 from the exponent. So what's the derivative of this going to be equal to? X raised to the what? Negative 11, right? You've got x raised to the negative 10 minus 1, so that's going to be x raised to the negative 11. So you've got multiply the whole thing by negative 10 times x raised to the power of negative 11 there. Yeah?
For the first example, that's assuming that x is in a constant.
Well, x is a variable. Yeah. So x and y are variables. If I'm using other like normal letters like A, B, C, then those are generally going to be constants. Yeah. All right. If you have a function that's not in the form you need it in, then you have to use your properties of exponents to get into the right form in order to take the derivative. So this is equivalent to x raised to the power of negative 10 based on properties of exponents. And then once you get into that form, then you take the derivative, doing what we did there. The square root of some variable is equal to x raised to the power of what? 1/2, right? The cube root is equal to x raised to the power of 1/3, right? So in order to take that derivative, you should get it into that form. So if you have a root function, you just want to turn that into x raised to the power of 1/2, and then take the derivative. So you multiply the whole thing by 1/2, subtract 1 from the exponent, so you're left with 1/2 x raised to the power of 1/2 minus 1. If you have this expression here, again, you need to simplify it in order to be able to take the derivative. So you've got x times x raised to the power of 1/2, which is equal to what? X raised to the power of 3/2, right? You've got the same base, and they're being multiplied. You have different exponents. So what do you do to the exponents? You add the exponents. You add the exponents, right? So 1 is equal to 2/2. So 2/2 plus 1/2 is equal to 3/2. And now you take the derivative. So 3/2 times x raised to the power of 3/2 minus 1. So you're left with 3/2 times x raised to the power of 1/2. All right, constant factor rule. If f is a differentiable function and c is some constant, then c f of x is differentiable, and the derivative of that constant times the function is equal to the constant times the derivative of the function, meaning you don't do anything to the constant, you just leave it there and then take the derivative of the function as you normally would. The derivative of a constant times the function is the constant times the derivative of the function. So 5x cubed. The 5, obviously, you just leave alone and you just take the derivative of x cubed. So 3x minus 1 from the exponent. So 3x, right, x squared. And then multiply the 3 times the 5, which gets you to 15. So again, you have the derivative of a constant times the function equals a constant times the derivative of the function. So you're left with 15x squared there. And again, what you're doing here is you're getting the equation for how that rate of change is going to change as you're moving along the curve. How that slope of those tangent lines to the curve is going to be approximated. That's why you get another equation, because that is changing. So you need to be able to account for that change as you're moving along the relationship. Sum or difference rule. So the derivative of a sum or difference of two functions, f of x, g of x, is equal to the derivative of the first function plus or minus the derivative of the second function. Example, 3x to the 5th plus the square root of x. So you just take the derivative of this term plus the derivative of that term. So you got, again, 15x to the 4th power there. This I simplified x. I just put that into the normal form, x raised to the power of 1/2 or x raised to the power of 0.5, same thing. So that's 15x to the 4th plus 0.5 times x, and then subtract 1 from the 0.5, so that's going to be 0.5 times x raised to the power of negative 0.5. So that's the derivative of this function here. You're summing two functions, so you just take the derivative of each individually. I just rewrote that there. X raised to the power of negative 0.5 is equal to 0.5 over the square root of x. All right, anyway, so that's the review of the derivative. If you're a little bit rusty on it, do what I said with the exponents. Like, look up a bunch of problems and just take a bunch of derivatives. I'm not going to ask you to do the product rule. I'm not going to ask you to do the chain rule or quotient rule. We're not going to use those methods here, but you should become familiar with them just to kind of have them in your utility belt. All right, now we can talk about the production function that is most common, that lies between the extreme cases of the linear production function and the Leontief production function, and that is what's called a Cobb-Douglas production function. The Cobb-Douglas production function does exhibit the properties we've been talking about, which is the increasing returns and the diminishing returns. The Cobb-Douglas production function takes the form of this. So you have capital raised to some power times labor raised to some power, where A and B are constants. Unlike linear production function, the relationship between output and inputs is not linear. Unlike the Leontief production function, inputs need not be used in fixed proportions. So we'll talk about the relationship between the variety, the varying of the two inputs when we get to the long run. The Cobb-Douglas production function assumes some degree of substitutability between the inputs, but not perfect substitutability. The amount that you can substitute them for each other changes along the range of usage over both inputs, which will become more clear when we get to the long run. Algebraic measures of productivity, average product, marginal product. How do we get that from this this production function? Well, the marginal product, when you take the derivative, average product is just normal, like look at this and divide it by the input that we're interested in. Suppose a consultant provides you with the following estimate of your firm's Cobb-Douglas production function, having done statistical analysis. The average product of labor is going to be your quantity divided by the amount of labor. So you're going to have the quantity, which is represented by the Cobb-Douglas production function, divided by labor. So you got here these terms, same term, exponents, one in the numerator, one in the denominator. So that's equivalent to L raised to the power of 0.5 minus 1, the power of the term in the denominator. So that's going to be equal to k to the 0.5 times L raised to the power of negative 0.5, because you're subtracting 1 from 0.5 there, which is equivalent to k raised to the power of 0.5 over L raised to the power of 0.5, which is equivalent to k over L raised to the power of 0.5. So just a bunch of different properties of exponents being used there. So that's one way you could take the average product from this production function. Another way, let's say you have, you're trying to figure out what is the average product of labor when 4 units of labor and 9 units of capital are employed. Another thing you can do is you can plug in the amount of labor and capital you have to figure out how much output is produced with those amounts of those inputs. In this case, it's 6 units. So that's your numerator. Divide that by the amount of labor, which is 4. So your average product of labor will be 6 divided by 4, which equals 1.5. So that's another way you could get the average product of labor, or you can just do it the other way that we did it. You have a formula already, and then you would just plug in the values of the inputs into it. So k over L raised to the power of 0.5, you plug in k equals 9 and L equals 4. And then just do a little bit of math, and that's going to get you to 1.5 again. And that basically tells you that at 4 units of labor, with 9 units of capital, on average, each worker produces 1.5 units of output. Marginal product for a linear production function. So for a linear production function, the marginal products are just going to be the coefficients on each of our inputs. So the marginal product of capital is equal to A. The marginal product of labor is equal to B. And really, we're just taking derivatives here. So one other thing that you should understand, I'm not going to expect you to do this, but when a function is a function of more than one variable, when you take the derivative, you take what's called a partial derivative. And when you take a partial derivative, you assume the other variable to just be a constant. So you're basically treating it like a constant. So if you're taking the derivative of this with respect to capital, labor's in here, but we just assume it's a number. And the derivative of a constant is just equal to 0. So taking the derivative of this with respect to capital, that's going to be 0. And then you're just left with this, right? K to the power of 1, multiply the whole thing by 1, subtract 1 from the exponent. K to the power of 0 is equal to 1. So you're just left with A. So the marginal product of capital, which is the derivative of this function, the partial derivative with respect to capital, is equal to A. And the marginal product of labor is taken the same way, but with respect to labor, and therefore capital is considered constant. And that's why it drops out when you take the partial derivative. All right, this implies that the marginal product of an input is independent of the quantity of the input whenever we're talking about a linear production function. Linear production functions don't obey the law of diminishing marginal product. The marginal product of an input for Cobb-Douglas production function does depend on the amount of the input used, as the following formula reveals. The marginal product for a Cobb-Douglas production function, just give me like 2 or 3 more minutes, and then we'll take like a 15-minute break. All right, so the marginal product for a Cobb-Douglas production function, if the production function is Cobb-Douglas and given by this expression here, then the marginal product of capital is what? Well, we'll just leave that answer till when we get back. I don't want to force this because I want to take a moment to clearly explain this. So why don't we come back at 8:30 and we'll continue on. Take a nice break and we'll continue going when you get back.